Black holes are the great consumers of the universe. They destroy everything, letting nothing escape once it has crossed the hole's event horizon. They get their enormous center of gravity from the fact that the collapsed stars concentrations of a huge amount of matter in a very small space. This pull they exhibit rips anything passing too close into elementary particles, sucking them inside their mysterious, dark core. But what exactly happens to all the matter and energy that the black hole consumes? It can't just as well be erased since our working knowledge of quantum mechanics forbids this. Our understanding consists of information existing forever in the law of conservation of quantum information. It is the very basis of quantum mechanics. Information itself is a specific arrangement of a particular number of particles, the way the arrangement of 2 hydrogen atoms and 1 oxygen atom gives us the information that this is water. According to quantum mechanics, if you could track all the atoms, particles, and radiation waves in existence, you would theoretically be able to see the entire history of our universe. So unless we rewrite quantum mechanics and general relativity, this information must continue to exist within the black hole. But, as Stephen Hawking showed with what is now called Hawking radiation, black holes evaporate and shed mass over incredibly long periods of time. This loss of mass would mean that information is lost forever. Hawking's findings were so controversial that it took fellow scientists a while to accept them and recognize their importance, eventually naming it the black hole information paradox. Before we get into the possible solutions to this paradox, there are a few more points to make about information and black holes. Once matter and energy enter a black hole, they add a small pixel of new mass at the point of entry. Incoming information would distort the event horizon at the point at which it crosses. The no-hair theorem says that black holes only have 3 properties: angular momentum, mass, and electrical charge. They should radiate at temperatures inversely proportional to their masses. But this Hawking radiation doesn't depend on what the black hole is composed of, instead radiating particles such as photons until there is no evidence the black hole existed to begin with. Just more empty space. There are a couple of possible solutions to the question of where does all this information go. The one which Stephen Hawking supported for many years involved having information disappear through a wormhole and come out in a different, parallel universe. It would do this by exiting through a white hole, the opposite of a black hole, constantly spewing information and unable to be entered from outside. While the information would no longer be accessible to us, it would still exist and thus still play by the law of conservation. The other solution is that information is imprinted on Hawking radiation itself so that it doesn't ever leave this universe at all. But how is quantum information transferred into Hawking radiation? By what mechanism does this happen? Even if there was a mechanism by which the data would imprint itself, it again violates the law of conservation because information cannot be duplicated. If the information both fell into the black hole and was preserved within it and it also existed on the surface of the black hole as an imprint on the radiation, that would mean that now 2 copies of that data exist. Some argue that the data is not duplicated because the timeline within the black hole is vastly different from the timeline at its surface, meaning that the copies don't exist at the same time, instead being entirely disconnected from one another. This is called black hole complementarity. And what about the mechanism for all of this to happen? When black holes store information, they are extremely efficient. They store information the way an iPod stores songs. A little handheld device can hold the equivalent of hundreds of CDs. That is, the information arrives and is transformed into extremely small pixels that distorts the event horizon. Those distortions contain information that could influence outgoing Hawking radiation, thus providing the mechanism. The implications of this are astounding. It means that the 3-dimensional interior of a black hole can be described by the interactions that happen on the 2-dimensional surface. If our understanding of quantum mechanics and general relativity is correct, the union depends on our universe being a hologram. The idea was even more fleshed out using string theory, leading to the holographic principle. Because a person inside a black hole wouldn't necessarily realize the 2-dimensional, that means that we wouldn't necessarily realize we're living in a holographic world. As of now, these are all still speculations based on science we're still developing. While general relativity and quantum mechanics have worked fantastically for us so far, we may have to revise them in the future to attempt to answer the questions our ever mysterious and ever complex universe gives us.